Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 2B, Part 4. We're going to call this Video 5A, and we're talking about the limiting distributions using moment-generating functions. And so in the last video, we discussed the theorem for the limiting distributions using moment-generating functions and found out that again, if the limit of the moment-generating function is the moment-generating function for a certain distribution, then the limit of the original sequence or sequence of random variables has a limiting distribution that is the same as the random variable or distribution for that limiting moment-generating function. We're going to use that to prove the central limit theorem in this video. So this is a very important proof. I hope you won't rush through it, because if you do, you're going to be lost when trying to do examples from this portion. You're going to need to copy down some of the numbered equations, and so you can use them in problems. Well, let's go ahead and get started. So it's important that we do the proof of the central limit theorem. So I need you to understand the steps in this. So I'm going to write this out in detail. So you'll need to make sure that you understand each step and can use these techniques in a problem of your own. All right? So the first thing we're going to do is we're going to consider e of e to the t w. Remember that w is equal to, we have shown previously that w is equal to, we've written this as the sum of xi minus n mu over the square root of n times sigma. We started out with, it's also equal to x bar minus mu over sigma over the square root of n. All right, and this has a so e of w equals 0, variance of w equals 1. Okay, so that's something to remember. So the moment generating function of w is going to be given by e of, now we need to rewrite, so we need to put in for w, substitute for w, so we're going to use this version here, and so we have e of exp, and I'll make a smaller bracket here, t over square root of n times sigma, or actually I like to write the sigma in the front so that there's no confusion of whether it's in the square root or not. So sigma square root of n under t, and then we have the sum of xi minus n times mu, and we need to close both of our brackets. Okay. Now we're going to write this out so that we're going to expand. All right. So we're going to expand this term here. So this is equal to e of, and we have e to the sigma square root of n t, and then I have x1 plus x2, this is all in the exponent, plus xn minus, now I have n mu, minus n mu, that means I have n of the mu's, and they're all minus, so minus mu, minus dot 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 minus mu, and there's n of these. Okay, so now there's n of these as well. So now I can pair up a minus mu with each of the x's. So, oh yeah, and so that's the end of the bracket for the expectation. So this is equal to e, bracket, e to the, we'll have sigma square root of n t, and then we'll have x1 minus mu plus x2 minus mu plus plus xn minus mu. Okay. So now I'm going to write this down here, and then I'm going to erase it. So here I have t square root of sigma times square root of n, and I'm going to make this like x1 minus mu grouped with x2 minus mu. So I'm going to group these like this, and this is what we're doing to get to the next step. And then I need to distribute this to each one of them. And so I'm going to end up with t sigma square root of n times x1 minus mu plus t over sigma square root of n x2 minus mu all the way up to the nth one. Okay? I'm not going to finish that because you can easily finish it. But that's what we're going to do with this next step. We're going to expand, we're going to distribute that constant here. Well, yeah, it depends on how you look at it. T times t over sigma times the square root of n. We're going to distribute that. And then when we have that, when we have e to the t sigma square root of n x1 minus mu plus t over sigma square root of n x2 minus mu, we can break this up as e to the t over sigma square root of n x1 minus mu times e to the t sigma square root of n x2 minus mu times e to the, and then you keep going, right? Okay, so that's the definition. This plus in the exponents means that we multiplied, right? So that's how we're getting to this next step. Okay. So this is equal to e of e to the t over sigma square root of n x1 minus mu times e to the t over sigma square root of n x2 minus mu e to the t over sigma square root of n xn minus mu. Okay. All right. And then, because they are independent, we can do the next step. This is only because they are independent. So this is equal to e of e to the t over sigma square root of n x1 minus mu times e of e to the t over sigma square root of n x2 minus mu expected value of e to the t over sigma square root of n xn minus mu, because xi are independent. Okay? That's the only way we can do that. If it weren't a random sample, we would have to know that they were independent. If they're not independent, this doesn't work. Okay? And now we know that they are identically distributed, so we can rewrite this, and we can just say xi. So we can change x1, x2, just put it to xi and say, because if I say that this one is also equal to e of e to the t over sigma square root of n x1 minus mu. It's the same thing because they're identically distributed. So I could replace them all with the same x sub I, okay, because they're identical. If they weren't identical, I couldn't do that. But since they are identical, I'm going to do that. So that is one of the tricks, or techniques, I shouldn't say trick. People think that there's something wrong with tricks in science, but it's one of the techniques that we use to show things. When they're identically distributed, sometimes we will replace them with the same variable since they're identical. And so this becomes e of e to the sigma square root of n times t on the top xi minus mu, and there are n of these. Okay? And this is because xi are identically distributed. Because it's a random sample. Remember, this is a random sample. So random sample goes to both, creates both situations. Okay? So now I want to let m of t, little m of t, sorry. I'm going to let little m of t equal e of, I'm going to write it as exp notation, and then I have t, and I'll have xi minus mu over sigma. And we're going to say that h is between, t is between negative h and h. So then this is the MGF of moment generating function of y I equals xi minus mu over sigma for I equals 1 up to n. Okay? Then I'm going to call this equation 6. Then e of e to the tw is equal to little m of t over square root of n raised to the nth power and negative h to t over square root of n h. Okay? And this is, so we're saying that because remember that that's what this is equal to here. This is, we've got t over the square root of n. All right? So if this little m is the function of yi xi minus mu over sigma, there's no square root of n there, then what all we're doing to get to from here to here is we're replacing t with t over the square root of n. Because sigma is already on the bottom, so we've just rearranged it. So this is the so this is e of tw is this. So this here is kind of a side. It's just a sub statement. Okay. So because of this, because we're letting little m of t be this, then we have we can rewrite e of the expected value of e to the tw in this form. Little m of t over square root of n, that quantity raised to the nth power. And again, we're replacing t with t over the square root of n. So in that statement, and this is similar to corollary 5.4 -1. So in section 5.4 of the text that we're using, that's similar to that corollary. Okay. Now, since e of yi is equal to 0 and variance of yi is equal to 1, so it's going to be e of yi squared minus e of yi quantity squared. This is 0. So it's equal to e of yi squared, which is equal to 1. It must follow, by logic, that, and we know this is always true, m of 0 is equal to 1, and m prime of 0 is equal to e of yi, yeah, I should use, oh yeah, so xi, yeah, so we're substituting in for y, so xi minus mu over sigma is equal to 0, and m prime prime of 0, remember this is the double derivative, second derivative with respect to t, is equal to e of xi minus mu over sigma quantity squared, and that has to be equal to 1. This is e of y squared, okay? And we're going to call this 7 in case we need it down below. Okay. So, similar to before, previously, we will use Taylor's expansion and a remainder after the second term or first derivative. Okay? So, what do we end up with? So we're going to have m of t is equal to m of 0 plus m prime of 0 t plus rn of t. And remember that rn of x equals f of n plus 1 derivative at c over n plus 1 factorial x minus a to the n plus 1. Okay? Now here, c is going to be equal to t1. If you remember from the last video, a is equal to 0, and we've got n is equal to 0. So this is r0, okay? And so we were able to write this as m of 0 plus m prime of 0 t, or actually this is going to be r1 this time. So similar, oh, that's not what I wanted to change. Okay, so n is not 0 here, n is 1. Okay? All right, so we're going to do one more term, and then we'll go with the remainder. So that's what we've done here, okay? The first derivative term, t. So how did we get this? Remember that Taylor series is the sum I equals 0 to infinity of f to the ith derivative of a over I factorial x minus a to the I. And so for 0, 0th derivative is the original function, which was m, and a is 0. So that gives us this first term here. And then for the second term, I is going to be 1, so we'd have the first derivative. And then we'd have t, and a is 0, so we're using t in place of x here. So we'd have t minus 0 raised to the 1, so that's just going to be t, which is what we have here. Okay? And then we have this remainder, and I can rewrite this remainder instead of rn, I need to write r1 of t. Okay. So then we can rewrite this, and this is going to be, since n is 1, n plus 1 is 2, so we're going to have the second derivative. And at c, that's going to be t1. And then we're going to have that over 2 factorial, which is 2, and then all of that times t minus 0 quantity squared, n plus 1, so that'll be t squared. All right? And so we can substitute in for 1, and then m prime of 0 is mu times t, the t here. And then we have m prime prime 0 over 2 I'm sorry, not over 0. This is t1 over 2 t squared. And now we're going to add and subtract t squared over 2 minus t squared over 2 plus m double prime t1 over 2 times t squared. And so we're adding 0. And then this becomes 1 plus t squared over 2. I'm going to group these two together. So I'm going to say plus the second derivative of m at t1 minus 1. I'm going to pull the t squared over 2 out to the outside. So the 2 is coming to the outside, and the t squared that's in both of these is coming out. So that just leaves a 1 there, a minus 1. Okay? Now, I'm going to substitute 8 into 6. So this we're calling 8. So this is number 8, and up here there's 7, and here's 6. Okay? So when we substitute into this, we have e of e to the tw is equal to 1 plus 1/2 t over square root of n quantity squared. So we're replacing t with t over the square root of n plus, and we're rewriting this a little bit. We can pull the 1/2. We can pull the 1/2 up to the front. Okay, so we're writing it as 1/2, and then we have the second derivative of m at t1 minus 1, and then we're replacing the t squared with t with t over square root of n, so quantity squared, and again we have t over square root of n is between negative h and h. And now we can rewrite this as 1 plus, and I'm forgetting something, this is e to the tw. Oh yeah, so we need the whole thing raised to the nth power. So don't forget that. We've got to have, we substitute inside. So this was little m, if you will. Okay? And so we have 1 plus t squared over 2n plus, we're going to put the 2n on the bottom, if I can write a 2n, and we have m double prime, can't read that, can you? Just had to do that, at t1 minus 1, and we'll use a bracket there, and then times t squared, and then the whole thing raised to the nth power. And now we've solved for t, so t, we multiplied all three sides of the inequality by square root of n, so we have negative h square root of n, and t is between negative h square root of n and h square root of n. Okay. Now remember, t1 is between 0 and t over the square root of n, and so when we take the limit, or as n approaches infinity, this term becomes 0. Okay? And that implies that t1 approaches 0 as well. Okay? Because it's squeezed in between 0 here, and this will be approaching 0 here, so it's going to approach, t1 is going to approach 0 as well by the squeeze theorem. Okay, so recall this, and that the second derivative of m at t is continuous at t equals 0, and t1 approaches 0, right? as n approaches infinity. Hence, we have the limit as n approaches infinity of m, second derivative of m at t1 minus 1 is equal to the second derivative at 0 minus 1, and we've already shown that this is 1, so minus 1, so that's going to be 0, and this is by 7 up above, which is here. Okay. Therefore, the limit of e to the tw as n approaches infinity is equal to the limit as n approaches infinity of 1 plus t squared over n plus, and this will be the second derivative at t1 minus 1 all times t squared over, this is 2n, sorry, 2n, and so this is equal to, I don't like how they did this, so let's make sure that we do this a little differently. So I'm going to rewrite this in the form to get an exponent, to get e raised to some power, if you remember. So this is going to be 1 plus, and now I'll have t squared plus m double prime at t1 minus 1, and then I'm going to put, let's see, so this is t squared, and all of this divided by 2 on the top, and all of that will go over n. Now, and this is all raised to the nth power, so I forgot the nth power here. Okay, so now everything that's in the numerator, this is b, if you will, and so this is going to be e to the b, if you remember. So, but now we're going to, so I can rewrite this as e to the t squared over 2. I'm going to distribute this half back in there, t squared over 2 plus, now I'm going to put the limit as n approaches infinity of 1/2 times m double prime of t1 minus 1. Okay, so this is all in the exponent, which is equal to e to the t squared over 2. Because remember, we just showed that this quantity goes to 0, or actually goes to 1. This goes to 1 because it's m. It goes to m prime prime of 0, which is equal to 1. Okay. So, and this is for all t in the reals, or in other words, we could say negative infinity to positive infinity exist. Okay, so it exists for all t, because this is defined for all t. It's all real t. Okay, and which is the MGF of a standard normal distribution, or a standard normal random variable, I should say. And this is in other words, a random variable with distribution n0, 1. Okay? Therefore, the limiting distribution of W equals x bar minus mu over sigma over the square root of n is equal to, we showed, sum of xi minus n mu over sigma square root of n converges in distribution to a standard normal distribution, which proves the central limit theorem. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.